Hello, and thank you for your interest in our work. The theme of our project here is combining observations from multiple instruments in order to retrieve the maximum number of geophysical parameters in the Arctic region. This project is a collaboration between the remote sensing departments at the University of Bremen in Germany and the National Space Institute at the Technical University of Denmark. The goal here is to support an upcoming ESA mission. This will be the CIMR satellite, a microwave radiometer which itself is needed as a component of the EU Arctic policy. It is a global coverage mission, but with orbit and channel characteristics designed with a focus on the polar regions. The launch horizon for this mission is planned for the mid-2020s. In short, with this project, we want to see how much can we get out of this upcoming instrument. We needed to evaluate the potential it has, especially what it can do better compared to instruments available right now. But how can we evaluate an instrument that doesn't fly yet? Well, as the design is built on existing knowledge, it is somewhat similar to existing instruments. So we used a combination of measurements from two very different but complementary satellites, namely the SMOS and the AMSR2 missions, to build our virtual CIMR construct. We took one set of channels which SMOS has at 1.4 GHz and we carefully combined them with 4 sets of channels from AMSR2 to create a consistent package of observations similar to what we would get from CIMR. The resolution improvement you can see in this table is a big part of what CIMR will do better than existing radiometers, but here we wanted to focus on specific geophysical sensitivities which the CIMR configuration will have. So we view our final results as a lower bound estimation for what CIMR would be finally capable of. Here are some example results which are presented in the poster. The first example is from the analysis we did for surface parameter retrieval, CIS concentration in this case, where we show that a combination of CIMR channels could match the best resolution we have today, but with a much higher accuracy. A combination of the 19 and 37 GHz channels from CIMR could achieve an accuracy level better than 5% at a resolution of around 5 km. Regarding atmospheric retrievals, and we show water vapor as an atmospheric parameter example, by combining input from all CIMR channels into one retrieval product, we can achieve a better precision than using single frequency retrievals. This is very important as the typical values for atmospheric water vapor load are very low in the Arctic, usually below the precision threshold for most passive microwave channels. In the final example, we show that CIMR could achieve a consistent CIS thickness retrieval which matches the performance of existing products but with fewer simplifying assumptions. Specifically, assumptions about a CIS cover in the satellite scene, which could be retrieved as a standalone parameter now. While we wait for CIMR, the methods we developed are ready to be implemented right now using the sort of instrument synergy demonstrated here, which would give us an 8-parameter retrieval for both surface and atmospheric variables in the Arctic. As a summary, we used a combination of AMSR2 and SMOS observations to evaluate the performance of an upcoming ESA mission named CIMR. We showed what benefits the CIMR configuration would bring for the remote sensing community, and on the way we developed methods which can be applied to combinations of existing instruments that would allow us to get a little bit more out of the data than what is possible by exploiting each instrument individually. Thank you very much for listening. I invite you to check out our paper that came out earlier this year for the full results. Of course, check out our poster and I will happily take any questions you might have.